6.5 Quantum Mechanics. Erwin Schrödinger developed a mathematical treatment into which both the wave and particle nature of matter could be incorporated. It is known as quantum mechanics. The wave equation is designated with a lowercase Greek psi. The square of the wave function gives a probability density map of where an electron has a certain statistical likelihood of being at any given instant in time. Solving the wave equation gives a set of wave functions, or orbitals, and their corresponding energies. Each orbital describes a spatial distribution of electron density. An orbital is described by a set of 3 quantum numbers. The principal quantum number, n, describes the energy level on which the orbital resides. The values of n are integers greater than or equal to 1. Angular momentum quantum number, L. This quantum number defines the shape of the orbital. Allowed values of L are integers ranging from 0 to n-1. We use letter designations to communicate the different values of L and therefore the shape and types of orbitals. If the type of orbital is an s orbital, then the value of the angular momentum quantum number would be 0. If the orbital is a p orbital, then the angular momentum quantum number would be 1, and so on and so forth. The next quantum number is called the magnetic quantum number, and it is symbolized by m sub L. The magnetic quantum number describes the three-dimensional orientation of the orbital. Allowed values are integers ranging from negative L to positive L. Therefore, any given energy level, there can be up to 1s orbital, 3 p orbitals, 5 d orbitals, 7 f orbitals. Orbitals with the same value of n form a shell. Different orbital types within a shell are called subshells. This table is very important to study. In the left-hand column, you see the value of n, 1, 2, 3, 4. You could think of these as the energy levels as you're going away from the nucleus. We also have the possible values of L. Since there's only s subshells in the first energy level, the value for the magnetic quantum number is only 0. In the second shell, you have 2 subshells, the 2s and the 2p. So your values for L are 0 and 1. In the third energy level, you have 3 subshells, S, P, and D. Your values for the magnetic quantum number are 0, 1, and 2. And then in the fourth energy level, you have 4 subshells, S, P, D, and F, with your L values of 0, 1, 2, and 3. Now the possible values of m sub L again deal with the orientation in space. Since the s orbital is spherical shaped, it only has one possible orientation, so they've designated that with a 0. Our p orbitals have 3 different orientations, px, py, and pz, and so it has 3 possible values of m sub L, 1, 0, and -1. We have 5 different d orbitals. So those 5 different designations for m sub L are 2, 1, 0, -1, and -2. And then there's 7 possible values or orientations for the f orbitals. So those values would be 3, 2, 1, 0, -1, -2, and -3. Now we already know that there's only 1 s orbital. There's 3 p orbitals, 5 d orbitals, and 7 f orbitals. We also should know that every orbital holds 2 electrons. So then the total number of orbitals in each shell will also tell us the total number of electrons in each energy level. Since there's only 1 s orbital in the first shell that can hold 2 electrons, the maximum number of electrons in the first shell is then 2. In our second shell, we have 4 orbitals, 1 s and 3 p's. Each orbital can hold 2 electrons, for a total of 8 electrons in the second shell. The third shell has a 3s. It has 3 p orbitals and it has 5 d orbitals. That's a total of 9 orbitals in the third shell. Each orbital can hold 2 electrons, which means that the third energy level can hold a maximum of 18 electrons. The fourth energy level then has 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals, for a total of 16 orbitals in the fourth shell. Again, each orbital holds 2 electrons for a total of 32 electrons in the fourth shell. Incidentally, there is a formula to determine the total number of electrons in each energy level, and that is 2n squared. Sample exercise 6.6, subshells of the hydrogen atom. Without referring to table 6.2, predict the number of subshells in the fourth shell, that is, for n equals 4. Give the label for each of these subshells, and how many orbitals are in each of these subshells. We are given the value of the principal quantum number n. We need to determine the allowed values for L and m sub L for this given value of n, and then count the number of orbitals in each subshell. There are 4 subshells in the fourth shell, corresponding to 4 possible values of L, 0, 1, 2, and 3. These subshells are labeled 4s, 4p, 4d, and 4f. The number given in the designation of a subshell is the principal quantum number n. The letter designates the value of the angular momentum quantum number L. For L equals 0, we have an s orbital. For L equals 1, a p orbital. For L equals 2, d orbital. And for L equals 3, an f orbital. There is one 4s orbital. When L is equal to 0, there is only one possible value of m sub L, and that is 0. There are 3 4p orbitals. When L is equal to 1, there are 3 possible values of m sub L, 1, 0, and negative 1. And there are 5 4d orbitals. When L is equal to 2, there are 5 allowed values of m sub L, 2, 1, 0, negative 1, and negative 2. There are 7 4f orbitals. When L is equal to 3, there are 7 permitted values of m sub L, 3, 2, 1, 0, negative 1, negative 2, and negative 3. Practice exercise. What is the designation for the subshell with n equal to 5 and L equal to 1? How many orbitals are in this subshell? And indicate the values of m sub L for each of these orbitals.